All right, so this page is going to start on page 18 of your packet. So we're going to talk about reflections and transmissions of waves. So if you recall, a wave is a transfer of energy, but not matter, through a medium. So we're not actually moving the matter itself, okay, from like left to right. What's happening is energy is being transferred from one particle to the next. Now, the amplitude of a wave is an indication of the amount of energy a wave is transferring. Waves with larger amplitudes transfer more energy than waves with smaller amplitudes. Okay, so think about a tidal wave versus a small ocean wave. Okay, so a lot of you have been to the beach. Okay, when they have that double red flag out, that means usually the waves are a little bit more bigger, a little bit more dangerous because of the energy it has. Okay, if it's just a small wave, it's not going to do much. Or something like a loud sound versus a soft sound. A loud sound has more energy and can do more damage. So two waves can have all of the same properties, frequency, wavelength, and velocity, but different amplitudes. So that means everything else stays the same, just the height of the wave can vary. Okay, so if we draw a diagram, okay, so there's my origin line. So I'm just going to draw a standard transverse wave. So remember, transverse wave looks like this. Okay, so remember you got your wavelength. So wavelength would be like a crest to crest. Okay, or a trough to trough. Okay, my amplitude is your height. So basically the height from the top to the bottom. Okay, no, not the bottom, or to the origin line. That is your amplitude right there. Okay, so basically what I'm going to do is I'm going to show you how everything else can be the same, but amplitude can be different. So I want the same number of wavelengths, the same frequency, same velocity, but amplitude needs to be different. So if I just basically, I'm going to make a smaller amplitude, and it's going to come through looking like this. Okay, so the exact same number of waves in the same amount of time. Okay, so everything else is the same, it's just the amplitude is different. Now there's a term called damping. That is a decrease in amplitude of a wave over time due to loss of energy. Okay, so as a wave travels away from one source, its amplitude decreases by damping, but its velocity remains constant. So that's a key thing there. So the velocity doesn't actually change. It's just the energy in the wave decreases. Okay, so I'm going to put this here. So velocity depends on medium. Okay, so if I have a wave going through water, okay, it can lose energy, but the velocity of the wave is going to stay the same. Now, if that wave goes from one medium to the next, that's how you can actually change the velocity. So if it stays in the same medium, you'll have the same velocity. So velocity does not change. Okay, if you change medium, so now you have a different medium. So like sound going from water to air or air to water, so different medium. Okay, means you can have a different velocity or it will change. Okay, so let's move on to the next page. Okay, so reflection. Okay, so there's a couple of links there that you can use if you want to, if you've got this access on Classroom. So consider a pulse moving through a medium. So remember that pulse is like that one little whip we send down a wave. Okay, perhaps through a rope or slinky. What happens to the pulse when it reaches the end of the medium? Okay, so the answer depends on whether it is fixed, meaning the end does not move, or it's just a free-floating end. So like if you just had a rope not attached to anything, and then you just send a pulse down. So the reflection of a wave is the transfer of energy back towards the driving source. So key thing is the reflection is what's coming back. So all reflections will be oriented as either right side up or upside down. Okay, so I'm going to show you a couple examples here. Okay, so let's say I have a rope attached to a wall and I send a pulse down. Okay, so the pulse is going to look like this. So it's just a wave. Okay, so this is your fixed end. So the end of that rope's not going anywhere. Okay, and so my pulse, my velocity is going towards the wall. Now, when that thing comes back, since it's a fixed end, what's going to happen is when it hits that wall, it's going to inverse. It's going to go the opposite way. So when it comes back, it's going to be upside down. Okay, so now my velocity, my pulse is going back towards the source, and my reflection, I'm not going to write this out, I'm just going to abbreviate it, is upside down, so USD, so upside down. So that is if it's with a fixed end. Now let's just say I have a rope that's not tied to anything, so I just send a pulse down. Okay, so there's no wall, so this is just a free end. Okay, so nothing's holding on to it. Okay, so whenever that wave or that pulse, okay, so we're going to send that velocity down. Whenever that pulse comes back, if there's nothing it's attached to, it's going to come back right side up. So it's just the exact same way as when it came down. So the reflection is going to be right side up, so RSU. Okay, so again, a free end means it's going to come back the same way. A fixed end means it's going to come back the opposite. So the orientation of the reflected wave will be caused by the wave entering a new medium with either a free end or fixed end. So the free end is the end of a material that is free to move around in space, okay, or is attached to a less heavy or less dense medium. So it doesn't have to necessarily be free, like not attached to anything, but let's say you had, let's see if I can make this a little thicker. Okay, so say I had a rope like this, so a rope this thick, and I send a wave down. Now let's say it's attached to a skinnier rope. Okay, so now that's the other part of my rope. That would still be considered a free end, okay, because you went from a more dense to a less dense. Okay, so when a wave is traveling through the free end of the medium, the pulse reflects off the free end and returns with the same direction of displacement which had before. So that just means it comes back right side up. So there's a couple examples of a free end. Okay, so sometimes you'll see this is basically where you have a rope coming down, you send down a pulse, okay, and then there's a ring, okay, attached around, let's just say that's a pole. Okay, that would still be considered a free end because this is still allowed to go up and down. Okay, so this is called your incident pulse. Okay, that is sent down towards the wall. So my reflected pulse, if this is a free end, so we're going to draw our little ring right there. So my reflected pulse is going to come back the same direction, so right side up. Okay, so moving on to the next, this behavior of non-inversion will always be observed when the end of the medium is free to move. Okay, this behavior of non-inversion is also observed when the medium is connected to another less or heavy dense medium. Okay, so that's basically what I just talked about up here is when you went from a thicker rope to a thinner rope. Okay, so that would still be considered a free end, so if that pulse would come back right side up. Now the fixed end is the end of the material that is connected to a fixed, unmovable position. When a wave is traveling through the fixed end of the medium, the pulse reflects off the fixed end and returns in the opposite direction. Okay, so again, that is just basically what we drew here. Okay, so we have our wall. We're going to send down our incident pulse towards the wall. And whenever it comes back, so there's my wall, whenever it comes back, it's going to be reflected upside down. Okay, this behavior inversion will always be observed when the end of the medium is fixed in position. So in conclusion, a pulse reaching the end of a medium does not become invertive whenever it is free end. Okay, so it comes back right side up. Okay, but when it's a fixed end, it's going to come back inverted or upside down. Okay, so that'll end that video.